Welcome to this explainer on the jacking control and monitoring system. If you're an offshore engineer or technician, you already know that the margin for error out on the water is practically zero. So this explainer is tailored specifically to give you total command of your rig. We're going to decode the exact systems that keep your platform standing, lower it safely, and most importantly, catch it when things go sideways.
Okay, let's take a quick look at the roadmap for today. We'll be running through 1. System architecture, 2. Redundancy and failsafes, 3. PLC and LED diagnostics, 4. Leg depth calibration, and finally, Resistor Bank modes.
Kicking things off with Section 1, System Architecture Overview. Let's map out the brain and the backbone of this operation.
Now, the command pathway here is actually pretty fascinating, and understanding it is crucial because to control the rig, you first really have to understand how it thinks. Your commands travel over an Allen Bradley Industrial Ethernet/IP protocol. The whole thing starts right at your dual Windows console PCs in the control room, runs through a master Allen Bradley ControlLogix 1756L73 PLC, which is essentially the absolute processing brain of the entire setup, and pushes through an Ethernet switch. From there, the data packets hit the point Ethernet modules down in the junction boxes. And finally, they reach the 20 E3 overload relays on each leg via a DeviceNet scanner. That pathway right there, that's the digital nervous system giving you high-speed, synchronized control over all 60 motors at the exact same time.
So it's an incredibly robust and lightning-fast network, right? But before we start talking about running it on a perfect day, we really need to ask the most critical question for your survival: what actually protects you when things inevitably go wrong?
That brings us right into Section 2, Redundancy and Fail-Safe Layers. Let's look at the ultimate safety nets.
This system is packed with some incredible survival instincts built directly into its hardware and logic. Check this out. If your master PLC drops offline due to a hardware fault, there's a second identical 1756L73 backup sitting right there in hot standby. It's continuously mirroring the primary processor, so it seamlessly takes over without dropping a single packet or interrupting the jacking process. What about a complete power failure? Well, the system doesn't just drop the rig. Instead, massive spring-applied brakes instantly catch and hold all 60 motors mechanically. And if just the control power fails, an under-voltage release automatically trips the main circuit breakers to prevent any rogue electrical anomalies from causing uncommanded movements. The rig is literally designed to fail safe automatically.
But here is the really crucial point to remember. Software logic has its limits. When things get really bad, you need physical guarantees. The emergency jacking system uses direct wired switchboard push buttons that completely bypass the PLC logic altogether. On top of that, the physical 24-volt DC hardwired e-stop cannot be overridden by any computer glitch, network failure, or software freeze. No way. When you slam your hand on that button, you are breaking a physical circuit. The hardware takes over instantly, and the operation stops immediately.
Moving right along to Section 3, PLC and LED diagnostics. Let's talk about reading the dashboard.
Look, if there is only one single thing you remember from this whole explainer, let it be this exact definition. A solid amber force light on your PLC means overrides are active. This means someone, probably during some prior maintenance or troubleshooting, has forced inputs or outputs in the programming. They've intentionally bypassed the natural safety logic of the controller. If you see this, you absolutely must not touch the jacking controls. Initiating a sequence with forced I/O can lead to catastrophic, completely unpredictable rig movements. You literally have to wait until a qualified programmer accesses the logic and removes those forces.
For day-to-day operations, the indicators are pretty straightforward. A solid green run light means you're good to go. Now, a solid red OK light during the initial power-up is normal. That's just the controller loading its project into memory. But a flashing red light on your PLC, that indicates a major recoverable fault. And a solid red net fault on your Ethernet modules means a severe communication error, like a severed cable or a duplicate IP address on the network. When you see red, it demands immediate troubleshooting. Almost always, you're going to start with a simple power cycle of the system to clear any temporary logic faults, and if that doesn't do it, you follow up by replacing the specific Ethernet communication module.
All right, so let's say your system power-up goes perfectly. You've got that green run light on the console, and you might be thinking you're immediately ready to jack up or lower down. But wait, what actually happens if you skip the mandatory startup sequence?
Let's unpack that in Section 4, Leg Depth Calibration. This is your mandatory startup procedure.
The short answer to what happens if you skip it, you are flying totally blind.
Every single time the console powers up, you must perform a calibration. If you fail to do this after a PLC restart, the system just defaults to an uninitialized reading of minus 11.0 feet. The PLC has absolutely no idea where the legs actually are in the water, and that makes any jacking operation incredibly dangerous because your automated limits and uneven load detections simply won't function correctly.
So how does the system know where it is? Well, it relies on an incremental encoder on motor A1 on each leg to measure relative position, but it needs you to give it the absolute starting point. To set the absolute depth, you just follow this sequence. First, navigate to the calibration screen. Second, press Enable. And then, this is the really crucial physical part of the job, visually confirm the actual 10-foot weld marks painted and welded onto the legs themselves out on the deck. Do not guess here. Once you have eyes on that physical marking and you've confirmed the exact draft, you enter that observed value at the console. Boom! Now your digital control system is perfectly synchronized with reality.
Okay, moving to our final section, Section 5, Resistor Bank Operating Modes. Time to talk about managing that lowering power.
Think about this. When you lower the rig, gravity basically turns your massive electric motors into heavy-duty generators. And all that massive electrical energy has to go somewhere safely to prevent frying the grid, right? That energy goes straight to the resistor bank. Autophase is your daily driver for this process. It's incredibly smart. It dynamically measures the negative power being generated, assumes you have a 200 kilowatt hotel load running to power the rig's basic functions, and rapidly phases the resistors to absorb exactly what's left over. It's perfectly efficient and requires absolutely no constant adjustment from you.
So, while autophase dynamically matches the required load for your normal operations, the other modes have very specific, narrow uses. Preset phase acts as a really solid backup if your power measurement circuit fails. It applies a fixed conservative resistance based simply on how many legs are currently active, though it does dissipate more energy than is strictly necessary. And then there's manual phase. You really need to ensure you stay completely out of manual phase, where a user inputs a manual 0 to 100% value. Unless you are specifically commissioning or testing the electrical equipment under very controlled conditions, just stick to autophase. Just a quick but absolutely critical operational aside to interject right here. Always, always consult your vessel-specific installation, operation, and maintenance manual before performing any maintenance, diagnostics, or operations we've discussed in this explainer. Every single rig has its own specific quirks, wiring schematics, and maritime class requirements.
When you step back and look at the entire architecture, from those hot standby ControlLogix brains to the hardwired physical failsafes and those highly intelligent resistor banks, the engineering behind this system is just incredibly robust. It really is perfectly designed to protect you. But remember, that design relies entirely on your strict adherence to proper startup calibration, respecting those LED warnings, and following operational rules to the absolute letter.
You now know exactly how the commands flow through the network. You know how the physical safety nets catch you, what those dashboard indicator lights are desperately trying to tell you, and how to safely bleed off massive power spikes during lowering operations. So the final question is, armed with a deep understanding of these jacking controls and redundancy systems, are you ready to step into the control room and take complete, confident control of your rig? Keep these technical principles in mind out on the water, trust your hardwired failsafes, never skip a calibration, and stay safe out there.